Hello everyone. In today's lecture we will be discussing wattmeter and energy meter. These both possess almost similar construction in the sense that each are having two coil system that are used for measurement, the measurement of current and voltage. So let's dig in. Electrical power is usually measured either collectively or in terms of some individual quantities such as current and voltage, whereas the power is the rate of doing some work, so its unit must be joule per second. So joule per second is termed as watt. Watt is a real power unit. Sometimes we are having some reactive components in the circuit. In that case we use the volt ampere reactive or volt ampere. This is the total combined power, whereas this is the quadrature power. So this is denoted by S, whereas this one is denoted by Q. Larger units may be kilovolt ampere, kilowatt hour, and kVAR. Sorry, this is kilowatt. There is no A in it. Kilowatt. So this is the unit of P. This is the unit of S, and this is the unit of Q. Okay. After that, we normally talk about power as the real power. So for that sense, we either convert the maximum current and maximum voltage by multiplying it with the power factor, or we simply multiply the amount of current and voltage responsible for producing heat, and this voltage and current are known as the root mean square values of voltage and current. So P can be IRMS VRMS, or it can be I max Vmax cos of theta. In DC circuit, the RMS values are similar to that of maximum values. So in DC circuit, let's say we are having some current, so that current would have the average value equal to maximum value, because there is no variation in this current with respect to time. So no variation means that I max would be equal to I RMS, which will be equal to I DC. Similarly, the case would be for voltage. So the voltage would remain constant, and VDC would be equal to VRMS, which would be equal to V max. With respect to time, it is the value of V. So in DC we say that P is equal to IV, and there is no Q in DC, and S is equal to P. So Q is not present in it, and S is equal to P. The total power is equal to the real power, and we can say that the value of cos theta is 1, because the current as well as the voltage are in same phase, so theta is 0 degree. So this gives us the value of RMS equal to I max. Okay. How we measure this power? Sometimes we individually measure I and V and then multiply it, because these are DC values. So let's say we are having some load in it connected in this circuit. So what we do, we first connect an ammeter with it and calculate our I, and then we connect a voltmeter across it, and then we calculate V, and this gives us our power, because the cos theta is 1. So this is the normal case for DC, but for AC we cannot just do that, because the maximum and the RMS are two different things. Okay. Sometimes we measure the effect of I and V combine on a same entity. So sometimes we use this mechanism combinedly. So in that case we might have some error in it as well. So in the next slide we will see that. Here we are having the error calculation, that we are having some resistance that is under observation, and we want to calculate the power across it. So we are using a general wattmeter. General wattmeter consists of a voltage measuring instrument and a current measuring instrument. It can be a coil, it can be a device, anything. It is a general device. So two methods. The first one is using a voltage in parallel with the resistance. So in this case, this voltage will give us a good voltage, but this ampere is giving us, this ammeter giving us bad current. Why bad current? Because the current going through this as well as the current going through this are calculated by this ammeter. So in this case we are having VRIS, whereas IS is the total current supplied to this one. So we must remove the current that is flowing through this resistance part. So the power indicated is actually the power consumed in this resistance plus the power loss in this voltmeter. So if we want to calculate the power consumed, what would we do? We will calculate the power indicated first. So I and V would be calculated. Now this I is IS and V is VR. So VR can be calculated directly. And then what will we do? We will subtract the amount of power that is consumed by the voltmeter. So voltmeter gives us this voltage of through it. So VR is given. So we can take square of it, VR square divided by the resistance of this voltmeter. So RV is the resistance of voltmeter. If we subtract this thing, we will get the good value, the value that is the real power consumption. Now reversing the case, if we have an ammeter here and voltmeter is here, so now the ammeter is giving us the good reading because the circuit current that it is calculating is actually the real IR, but this voltage calculating device is calculating the voltage across ammeter and across the load. So there are two voltages that it is calculating. So the power indicated is actually power consumed by this load and power consumed by this ammeter RA. So what we can do is that we have already calculated the I across this. IR is calculated. So if we calculate the total voltage across this circuit, that voltage would be Vs. The total current that is flowing through this ammeter is Is. So this is giving us the total power indicated. Now we want this consumed power. So subtract the power that is lost inside the ammeter. So what is lost inside the ammeter? The Is square and Ra is lost. So IR square or Is square into Ia is subtracted from it. So I guess this is pretty much clear that if we want to calculate the power across this load, what we will do is that we will calculate the total power and then subtract the loss power. Okay, here I have written a sentence, the equivalent resistance changes for each path while connecting type A or type B. So this is type A and this is type B. This states that the equivalent resistance which is seen from this source will change by replacing these two instruments with one another or by changing its order. So let's say we are having two resistances and one resistance is here and other is here. this will have different effect if one resistance that was here is here and the resistance that is here is replaced here. Now if we have some load in here, that will have some different effect. So on this scenario we are having a problem in this course. So just go to that problem and you will know that what are the percentage error that occurs while replacing these two sequences using type A sequence and then type B sequence. So just go through this problem and you will know that what is the difference between the connection type. Moving towards the power measurement in AC. So we studied that in DC P is equal to I RMS, V RMS is equal to I max, V max is equal to I indicated, V indicated. So all things are equal and equal to S, whereas Q is equal to 0. Now in AC, AC involves Q, the quadrature power. So what will happen? The real power would be either calculated from the heat dissipating measurement units such as IRMS and VRMS, or it can be calculated from the maximum values such that we know the difference between the angle of current and voltage. So in that case the current and voltage were flowing in the same phase and the theta was 0 degree. But now the current and voltage would have some lead or lag effect. So in that case there would be some theta with it. So let's say this is our voltage and the first one, this one is the current. So VI cos of theta would give us the P. So P is equal to I V cos of theta. These things are phasor. So in phasor we write these maximum quantities over here. Okay. Now if we want to calculate the total power, so total power can be calculated from the instantaneous value of the voltage and current. As the voltage increases and then decreases and the current increases and then decreases, so multiplying here and here would give us different power, but here and here would give us some different power. So instantaneous power would be always different, and this power is denoted by PT, where this is the total power of the circuit as well. So this is not resistive power, it is the combined power of both reactive components and resistive component. So this is the story of power in AC. We calculate the power in AC by either electrodynamometer type instruments or by calculating with AC meters. So AC meters are known to us. Let's talk about this electrodynamometer. In electrodynamometer, when the AC current changes in this component, let's say, the current also changes in this component. So if the current changes like this, the magnetic field is in this direction and the magnetic field in the coil is in this direction, so it would interact in the same way as if the magnetic field in the CC coil, the current coil, is in this direction, and in the potential coil it is in this direction. So both will have same effect. So this is the theory of electrodynamometer, that we are having some current coil and some pressure coil. PC means potential coil or pressure coil, because voltage acts as a pressure. So more voltage, more current would be causing to react with it. Okay, so the net effect would be multiplicative. Okay, its construction is simple. We have fixed coil system. The fixed coil system are here and here, and we are having moving coil system. The moving coil systems are in here, and we are having moving and restoring system. So moving and restoring system are actually the spring spindles which causes this thing to rotate back